Greeting physics fam. We are looking at 7-2, potential energy and kinetic energy worksheet. Let's look at numbers 8, 9, and 10. If we start with number 8 here, it says a flea gains 1 times 10 to the negative 7th joules of potential energy. So right away, potential energy is given to me, 1.0 times 10 to the negative 7th, and that's in joules. It says the flea jumps this high, so the height is going to be 0.03 meters, and we know that the height off the ground is related to the potential energy of an object when we talk about gravitational potential energy, that is. Perfect. And we want to know what the mass of the flea is going to be. So that is our unknown. Luckily for us, we know the equation for potential energy due to gravity is mass times gravity's acceleration times height. So all we need to do is start plugging in for that, and we can do that. We know potential energy, it was given to us, is 1 times 10 to the negative 7th. We are going to solve for mass, so that's going to be our variable. Gravity, we know its acceleration is 9.8. In this case, I am ignoring the negative, the direction. Don't get too mad, but we're ignoring it for right now. No big deal. We're still going to get the same quantitative value. And then the height is going to be 0.03 meters off the ground. Now, when I start solving for this should be pretty straightforward, but I'm going to take the 9.8 and times it by 0.030. When I do that, I end up with 0.294, and I'm still going to carry down my variable. That's important. And I still have 1 times 10 to the negative 7th on this side. Now to solve for my mass, I'm going to divide both sides by 0.294. And the reason I'm going to do that is m will now be all alone by itself so that we can solve for it. And all we have to do then is 1 times 10 to the negative 7th divided by 0.294. The answer you get has a lot of zeros. It's 0.00000034. So let's put that into scientific notation. That's going to be 3.4 times 10 to the negative what power? Let's see. I'm going to move my zeros 1, 2, 3, 4, 5, 6, 7 places back. So it's going to be times 10 to the negative 7. So 3.4 times 10 to the negative 7th, and that's in kilograms. Now, it's a flea, so should it be really, really tiny? Yeah, for sure. It should be light, so the mass makes sense to me. But I solved for that all because I understood the gravitational potential energy and used the equation. Nice job. All right, let's move on to number 9. At target practice, Scott holds his bow and pulls the arrow back a distance of 0.3 meters. So, okay, right away we have a distance of 0.3 meters. And we're exerting an average force. Oh, okay, we've got force here. Now remember, force times distance is work, so I wonder if we're going to do something with work here. We've got a force of 40 newtons. We want to know what the potential energy stored up in that bow is going to be for the moment before that arrow is released. All right, so we have our givens and we have our unknowns. The question is, what formula are we going to use? Well, if you remember from notes, the energy work theorem, the amount of work you do on an object is equal to how much the potential energy will change. So if the object had no potential energy to start, but now gets pulled back, whatever work you do on it, that's the potential energy it's going to have. So we can kind of combine these two. We know that work is force times distance. We know that already. And since work is going to be equal to potential energy, that's going to solve for it. So literally, this is just going to be a work problem. And when you solve for work, it's going to be equal to the potential energy. Again, because of the energy work theorem. All right, so let's solve for this bad boy then. This is really straightforward. We're just going to do 40 newtons times 0.3 meters is going to give us our potential energy. Throw that in your calculator, and that will solve it. And 40 times 0.3 is really just 12. Now, what are the units for energy? It's joules. So, awesome. Remember that work is not only measured in joules, but so is energy. So that's why energy and work kind of flow between each other. By doing the work on the object, you gave that bow the stored up potential energy. That's what the energy work theorem talks about. All right, that sounds good. That was pretty straightforward. Once we realized that once we solved for work, it became potential energy. Let's look at number 10 to finish off our worksheet. A 0.08 kilogram robin. So first of all, something's given to me right away. The mass of a bird. Don't know if I'll need it, but I'm going to write it down because it's given to me. It's perched on a power line 6 meters above the ground. All right. 6 meters above the ground to me sounds like height related to potential energy. The bird swoops down and snatches a worm from the ground and then returns to an 8-meter high tree. Oh, okay. So it looks like the initial height of the bird is 6 meters, and then the final height of the bird is 8 meters. Ooh, okay, that's interesting. So how much did the bird's potential energy increase in its trip from power line to the tree branch? All right, basically meaning the bird started, oh boy, I can't draw very well. There's your bird. Started at 6 meters off the ground and ended up at 8 meters off the ground. So basically, how much did potential energy increase by? So we really want to know what the change in potential energy is. Now remember, whenever you have a change in, you always take the final of that object minus its starting initial. So if we know the initial and the final potential energy, we can just subtract them and find the change in. That's at least for part A. So let's do that. No problem whatsoever. So I'm going to take my starting potential, my final potential energy. I know potential energy is mgh. Okay, so I'm going to take mgh and I'm going to subtract the initial mgh, and that will give me my change in potential energy. Now, it's height 1 or the initial, forgive me, whoa, I'm a mess here. You have to start with final. Got to listen to my actual notes that I'm writing in front of me and subtract the final height. Now, if this is overwhelming you, just relax. Take a step back. Remember, the change in anything is final minus initial of that. So all we're doing is we're taking two different potential energies, no big deal, and we're going to subtract them once we solve for them because that's going to tell us how much potential energy changed when the bird went higher. So let's start substituting in. You're going to see this is no big deal. All right, the mass of the bird doesn't change, so it's 0.080 on both sides. Gravity is 9.8 meters per second on both sides. And the final height of the bird is going to be 8. So we just plugged in for this part of the equation. We're good there. Now, the mass of the bird, again, is 0.080. Gravity's acceleration is 9.8 meters per second. And the initial starting height was 6. So let's put all this together. I'm going to go in red so that we can help figure this out a little better. And let's subtract and see what we can get. So first I'm going to do 0.080 times 9.8 times 8. In my calculator, that gives me 6.272. Now I'm going to also calculate 0.080 times 9.8 times 6. And that gives me a value of 4.704. Now remember, the initial was 6 meters off the ground, so that makes sense that the potential energy is less initially than finally because the final height is 8 meters off the ground. So this makes sense that this first number is bigger. But when I subtract the two, all I'm doing is taking 6.272, which is the final potential energy of the bird, minusing its 4.704 starting potential energy. And when you subtract the two, you end up with about 1.57 joules. So what does that mean when we subtract it? The change in potential energy, meaning between what it started with and what it ended with, the potential energy increased by 1.57 joules. And there you go. So we're kind of looking at our different ideas about energy and also applying the knowledge we have about things like when it changes, like change in temperature from chemistry was always final temp minus initial temp. So we just used that skill and it helped us figure it out. All right, nice job, physics fam. We completed this. Hopefully we're getting a little bit better of an understanding between work kinetic energy and potential energy. They're all related, and we need to keep pushing forward to make sure we see those connections. Be well.